Hi, my name is Cameron DeCamera, Principal Engineer at Microsoft, working on the Visual C++ compiler. Today we're going to talk about some common myths or misconceptions around C++ modules and give you some practical advice on how to move forward and move past these things. So without further ado, let's get right to it. Okay, let's start with a little bit of motivation behind why I'm giving this talk. The first thing is that modules currently struggle with widespread adoption. This is for a multitude of reasons, least of which being build support, but that's actually improving nowadays. However, there's still kind of like some misconceptions around how modules actually work. The other thing is that as I mentioned, we struggle from misinformation. And so the goal of this talk is to kind of take some of the common misconceptions that we've seen and sort of debunk them and, myth bust them, if you will. Modules really does have a bright future, and it's not just for compiling code. It's really for tooling, and I've talked about this in the past as well. And I also want to provide practical guidance for some of the unknowns that people have run into. So we're going to talk about some of the common breakage you might see with modules and how to possibly move past that. Okay, so let's dive into the myths, shall we? And here I have a picture of Plato. Plato believed that knowledge is contingent on our ability to discover it. And my goal with this talk is to arm my viewers with the knowledge of how to move past these myths. But really, to call them myths is a little misleading, and what we're really going to cover here are common misconceptions. However, misconceptions is a little less of a pithy title, so we're going to stick with myths for now. And the first myth that we're going to cover is strong ownership is not necessary. Okay, so to understand strong ownership, let's dive into a little bit of the history of strong ownership. This began back when Gabriel Dosray first created the modules TS, and he added this bullet point in the one definition rule. This essentially is telling the implementation that it is allowed to attach ownership information to declarations that appear inside of the module. He later elaborated on this idea in his CPPCon 2015 talk, Large Scale C++ with Modules. He talked about how this ownership information should be attached within the toolset and the safety it allows for library authors. So why does it actually matter, though? This is what we actually need to know as library developers, right? So library authors get better control and safety over function names that they export. Because this ownership information is attached to the declarations inside of your module, it means that it can't clash with other declarations that appear in other modules or declarations that appear in the global module. It also creates a migration path from headers, and we'll talk about this in the demo portion, which is right now. So here's an example of a simple program where we have one module named M1 and a main in main.cpp. All we do is we call this function called the answer, and we expect it to be 42. If it's not, we return 1. Right? So if we compile and run this program, we expect it to return 0, since the answer is equal to 42, and this will not be hit. And indeed, our program does return 0. So strong ownership allows us to have sort of module level linkage in the sense that the names of the functions start to matter a little bit less, and the actual ownership of them matters more at the link step. So if I look at this other module I have here called M2, we have a function called the answer, except this time it returns 41. You'll note that it has the exact same signature as our module M1 version does. In a traditional C++ compilation scenario, this would be a classic ODR violation. I have two copies of the same function with the same name and signature, and they are both defined in separate translation units. However, with C++ modules, we kind of get a pass for this due to strong ownership. So if I have a library here, this is just another C++ file where I import M2, and I create this function called libanswer. And all I want to do is I want to forward declare this thing inside of my main and call it except this time we expect it to be 41. Now we should be able to compile and run this entire program. And indeed it does compile. If we run it, we get the expected 0. And why did this work? This worked simply because of strong ownership. We have 2 copies of the answer. However, one is coming from module M1 and one is coming from module M2. And the strong ownership information, it enables the linker to resolve that conflict at link time. Another important thing to know here is the level of safety that this gives you now with as a library author, in that you can create situations like this much more safely than you could before. And in fact, in a lot of the cases, you wouldn't be able to create a program like this, or if you could, it would likely result in weird runtime behavior because the linker might select your function or it might select another function of the same name. So if we take the strong ownership idea a little bit further, we actually, in the MSVC toolset, we allow the linker to fall back to weak ownership if it can definitively prove there is only one strong owned symbol of that name. So let me give you an idea of what I mean here. If I get rid of this lib answer and I get rid of this, and we just have the answer here, but let's say this came from an older version of the library that you want to combine with the modularized version. So if I just have a forward declaration here, like this, and I get rid of the import, so this is the entire program now. We're still compiling both modules, M1 and M2, except this time the linker is only going to have the information that there is some function called the answer somewhere. So let's try to find it. You'll notice that the linker came up with this ambiguous symbol lookup. And that's actually expected because there are 2 of them. But what happens if we actually exclude one of these from the build? So let's exclude M2 here. If we exclude M2 and we attempt to rebuild again, if we exclude M2 and the library, because we no longer need the library portion, we can try to run, and we can see that this actually succeeded. And the reason is because the fallback to weak ownership, if the linker can prove there's only one of these in the entire program, which it did since we excluded M2. If we run this, we get our expected 0 output here. And this is what I meant when I said that it gives libraries the option to migrate away from headers and still retain strong ownership guarantees with a named module. So you can combine header information with this strong ownership information and still get client programs to move forward. And 2 last things to note here is that 1, you can disable this fallback mechanism. There's a linker switch for that. And 2, if we did define this to be something else, and we attempt to rebuild our program, right, we do get a successful build result, and if we try to run it, we get the expected output of 1, because the linker is no longer using our strong ownership symbol, it's using this one, and not the one that came from the compiled module. It's still there in the OBJ, however, the linker does not select it because we have an exact corresponding declaration for the use of this thing. Okay, swinging back to our slide deck, coming back to strong ownership, we actually see that Clang and GCC have also come to the same conclusion that strong ownership is necessary for the success of C++ modules. This is an active pull request out to the Itanium API, which adds the name mangling necessary to make strong ownership work. Furthermore, I gave a talk back at CPPCon 2021 with Gabriel Dosray, where we covered the compiler internals and the implementation details of strong ownership in the MSVC toolset, basically how the information is conveyed through the toolset to the linker to make this feature actually work. So if you're interested in the implementation details of that, I highly recommend watching that talk. So I hope now that gives you sufficient evidence to come to the conclusion that strong ownership in C++ modules is actually necessary to make this thing succeed. And we're talking about named modules in this case. So that's kind of our first myth, and this is the confirmation that we have. So strong ownership is necessary. So let's go to the second myth, right? Hash include after import is an insurmountable problem which blocks adoption. And this is a common problem that we've seen from many customers, from many different compiler implementations. This is an ongoing problem that we need to solve. So let's try and solve it. So let's kind of start with a problem description. If you're unfamiliar with what this problem is, it kind of boils down to this. So let's consider this translation unit. We have import std and hash include print, which is the C++23 library, the format library. And we try to print line hello world. So if you go to compile this, this is the set of errors that I got from Visual Studio when I tried to compile this thing, right? There's a whole bunch of redefinition errors, but what do those actually mean? Let's try to focus on one of them, right? So std remove reference is a class template that is already defined. Conceptually, what the compiler is seeing from this is this kind of translation unit, right? So we have import std and hash include print. To the compiler, below that comment, we see std print line definition and then another copy of std print line. And if you were to just write this in a regular translation unit, this would be a classic ODR violation. However, the standard tells us that this is supposed to work from an implementation perspective. So as a user, you want this to just work. However, to the compiler, it just looks like an ODR violation. So what are we supposed to do? The standard actually has a little trick up its sleeve that we can leverage in order to resolve this problem. And it's called include translation. What it does is it enables us to take this translation unit and rewrite it like this. So we have import std, and we have import print instead of the hash include. And we didn't actually have to change the translation unit at all. This happens under the covers. The compiler is rewriting that hash include statement for you. So let's see a demo of what this might look like and why this actually is important for resolving this bug. So here we are back in Visual Studio to talk about the problem. If I take that translation unit that I showed you before and I try to compile it, we actually get the very same compiler errors that I showed you before, right? So we have the redefined class template issue. So what we need to do is we need to take this include and somehow translate it automatically for us. And the way that we can do that is we first need a target to translate it to. And how I did this is I created this import std.h, and all it has is this. So we're going to deduplicate all of our standard library headers to import std, essentially. That's the idea. And to make it a target, we just change the configuration property of this to C and C++ compiler. And that tells MS Build, hey, this is actually a header unit you need to build as a prerequisite to building the program. And finally, we need to do one more thing. We need to go down to C++ properties and enable translate include. And one last thing is that we need to add this line to our compiler options. This tells the compiler that the print header actually points to the IFC that we just made the build system create for us. So now if we go back to our main and we attempt to recompile again, we actually get a success this time. And if we try to run it, it runs hello world just like we expect. And you could do this with any number of compiler headers. So we can do include iostream, for example. We can include vector. And as long as we keep adding those lines to this build line here, so we want one for IOStream, and we want one for vector. And if we build again, we could see that our build was successful again, because all the compiler is doing is it's taking all of these headers and translating them to our import std h. It's translating it to this. Every single one of these, and that completely sidesteps the duplicated problem. Now, you still have an issue where you might want macros from some of these headers, and in those cases you can either add the macros here, or if instead of using import std you actually want to use the real header information, then you can just hash include all the headers in here and translate them that way. And this is actually what we did for the Office build when we moved to using header units to build Word. Speaking of Office, we went through a series of blog posts where we detailed our experiences in migrating a very large code base to use header units and eventually to name modules. This is a very good guide for anybody with a code, like a code repo of this size, looking to experience in the problems that we ran into, the category of issues, and how we solved each of those problems. And this include translation mechanism that I just showed you is actually one of the things that fell out from that investigation, and one of the learnings that we had in creating a path from textual inclusion to now a modularized and sort of like data-driven approach with these IFCs on disk. Swinging back to our slide deck now, we've gone through the exercise of making this work in Visual Studio. Now, this is not a solution that will work for every build system. Obviously, things like CMake need support for include translation in order to make that approach work. But as long as your build system has some support for include translation, you can actually create a situation where this problem is no longer an issue. So if we go back to our myths now, we can safely say that include after import is not an insurmountable problem blocking adoption, right? And finally, we come to our last myth. C++ modules do not improve build times. This is by far the biggest thing, the biggest question mark in all of modules history. So do they actually improve your build times? Because that's what a lot of people want to get out of them, is better build throughput. And, you know, despite the fact that we've covered things like strong ownership, which are an additional guarantee that you can't get out of hash include, people really just care about the build times a lot of the time. So how do we get better build times out of C++ modules? And what makes the compiler go fast, right? The thing that makes it go fast is the removal of textual inclusion. If you can take parsing out of the equation, the compiler will go very quickly. Reducing disk activity, specifically on Windows, disk activity can be kind of expensive depending on what thing you're trying to hit, what thing you're trying to access. And oftentimes hash include hits this problem where you have to go hit a file, read that file, and then there's another hash include inside that file. But this also applies to modules in that you don't want to read more modules than is strictly necessary. And we'll talk more about that in the demo portion. And finally, you want to reduce template instantiation, because template instantiation is not something that modules can really shield you from. If you have to specialize a template, the compiler still has to go through the process of specializing that template and instantiating whatever members of maybe the class template and perform overload resolution and a lot of semantics elaboration that come along with template instantiations. So without further ado, let's jump into the demo and see what we can do about build times. A few years ago now, I created this blog post where I took a project that I had created and it was using traditional hash includes, and I rewrote it to use name modules instead. And so I went through that process of describing the problems that I ran into and how I fixed them, and finally a couple of build results on how, what the performance was at the time. This, remind you, this was many years ago, and today things are in a lot better shape. And finally, this also used CMake and a very early form of CMake. Now we can use more modern CMake facilities. For example, we can build with Ninja now instead of just Visual Studio 2019. So I'm going to go ahead and clone this project and build it without modules, show you the build times, and then I will build it with modules and show you the build times and see if there's some kind of measurable difference or if they're worth pursuing at all. So I went ahead and grabbed that repo and cloned it locally. So let's go ahead and use CMake to configure and build this project so we can sort of get an idea of what it looks like without modules first. So we're going to use Ninja as our generation target, and we're going to add a build folder. Okay, so that's done. Let's build it. So we see here that there's a whole bunch of information that was spit out. So let's kind of clean this up a tiny bit. Let's only modify this file. So I'll add a little bit of white space. And let's go back to here and see what it looks like if we just build that main file. So the thing we want to pay attention to here is the number that was spent in the front end. So that's c1xx.dll, right? We spent 1.3 seconds just building this one file. So that's an example of how long that took. And I'll do a side-by-side of the end-to-end build at the end with the non-modules one and the modularized version, just so you can kind of see what an end-to-end build looks like instead of just the inner loop. So let's switch over to the modules version. So now let's see what CMake looks like here. So let's remove the old configuration directory and let's reconfigure and rebuild. So let's go ahead and build. So you can see it wasn't that much longer than the like the end-to-end build, including building all the IFCs, wasn't that much longer. But let's take a look at what it takes to rebuild this thing now. So if I make a white space change again, and I come back here, and I say CMake build, right? Now we're seeing some pretty crazy speed up. We see that we went from 1.3 seconds to 0.11 seconds. That is an actual 10x speed up from using name modules over not using name modules and using traditional hash includes. And if you're still wondering if the behavior of the actual application is the same, we can go ahead and go into build here and ballpit.exe, right? It functions exactly the same with modules and without modules, right? So we built the same program just at 10 times faster. And so I realized that was a little bit of a smaller project to kind of sink your teeth into, and it might not be illustrative of larger programs that are not built with CMake and built with other various build systems such as Bazel. But if we kind of look again at the experiment that we did with Office, and we come back to that build throughput graph, we ended up seeing experiences where the module build was actually up to 20% faster than using regular PCH. So we took a technology which was roughly 30 years old at this point, and we improved it to the point where we could make the header units actually faster and more efficient in other ways than header unit or than the PCH ever could be. So if we scroll down to the additional advantages section, we can see that the sizes of the on-disk artifacts is significantly reduced. And this is what I was talking about, where you want to reduce your on disk IO because the compiler does have to read the entire PCH. It has to memory map that in order to make things work. And the same thing is true of the IFC. However, the IFC is roughly 10 times smaller than that of the PCH in almost every case. So the fewer of these things you load in, the fewer memory maps you have to perform, the better your overall throughput will be. So let's come back to our deck one last time. And finally, we have tackled the last myth of C++ modules do not improve your build times to C++ modules do improve your build times. Definitively, we've proven it. And obviously, your mileage may vary there, but in our experience, as long as you're doing things in a way that's very modules friendly, you tend to get this really good throughput benefit. And thank you for joining me today. I hope you were able to learn something that you can take with you and sort of move past some of these common misconceptions that I have gone over with C++ modules. And maybe you can help in the adoption of modules yourself on your own projects and sort of move forward with the benefits of name modules. And thank you all again.